All right, everyone, it is quarter from the hour and we are live, so let's get started. First off, thank you everyone for joining us today at the 2021 TMLS Annual Conference and Expo. I hope you are enjoying the amazing session so far. Before I introduce our next speaker, I'd like to just give a quick reminder to check out our sponsor booth, which you can navigate to by clicking the booth icon to your left. Once you're there, you could click into any of the booths to learn more and also enter for a chance to win some cool swag. Now, without further ado, I'd like to introduce our next speaker, Emmanuel Rossi. Emmanuel is a machine learning researcher at Twitter, as well as a PhD student working on graph neural networks at Imperial College London, and supervised by Michael Bronstein. Before joining Twitter, he worked at Fabula AI, which was acquired by Twitter. Previously, Emmanuel completed a Master's of Philosophy at the University of Cambridge and a Bachelor's of Engineering at Imperial College, both in computer science. Emmanuel will be giving us a talk on graph neural networks with almost no features. Please give a warm welcome in chat.
Thanks a lot, Peter, for the introduction. Okay, so yeah, let's get started. So actually change the title a little bit to graph neural network with missing node features, and we'll see in a second why. But let's start with some motivation for this talk. So why do we care about graphs and in general, learning on graphs, and in particular, why do we care about having missing node features in a graph? So first of all, regarding why we care about graphs. The reason is quite simple, is that networks are kind of everywhere in the world. They can be observed everywhere. And graphs are the perfect mathematical tool to model networks. So graphs are just, a pair of vertices and edges, and they can be used to model perfectly all these networks. So here we have some examples, clear example, and quite widespread at Twitter is a social network where you have users which are connected by some sort of friendship or relationship. But also molecules are kind of perfectly represented by graphs where you have nodes being atoms and the edges being the chemical bonds between them. Interesting applications are also functional networks of the brain. So we have edges between different areas of the brain, which are active kind of together. But also interaction networks such as protein interaction networks, where we again have a connection between proteins which are kind of related or are active at the same time. So now that we're interested about graphs, we also want to do learning on these graphs. One of the big success stories in machine learning and deep learning has always been computer vision. So learning on images, and so we will kind of derive and motivate the learning on graphs, and we will see that it's very similar to learning on images with some additional constraints and challenges. So on images, two of the classical tasks that you can think of are image classification, where you have an image and you want to predict a class for the whole image. So you want to assign a class to the whole image. In this case, we want to say, okay, this image contains a cat. Another type of task is what is called semantic segmentation, where we actually want to segment the image in different parts. And what we're basically doing is assigning a class to each pixel. And so we're saying, okay, this pixel belongs to the road, this pixel belongs to a car, and so forth, and so on. But we can think of as almost as being a pixel-wise classification, pixel-level classification. And basically, we can see that there is a very close analogy to the task we care about in graphs. So in graph, you may care about doing graph classification. And when I say classification here, you can always replace it with regression, but to keep it simple, let's say classification. Graph classification, we want to predict some global property of the graph. So for instance, in a molecule, we may want to predict whether it is drug-like or not. If, for instance, we're doing drug discovery. We may be interested in node classification, where we want to predict a class for each node in your network. So if these are users, you may want to predict, for instance, the gender of the user, let's say. And we know, the labels, the gender for some of these users, and we want to predict for the remaining in our network. Another common task is limb prediction, where we basically want to predict which links are missing from the network. So which links should be there but are not there. So for instance, in a social network, which users should be connected, but they are not yet. So now that we saw that there are very similar tasks, the analogy extends further in the sense that also the kind of techniques that we want to use are very related. So on images, we know that the kind of one of the best performing models. I mean, nowadays with Transformer, this is kind of changing, but the kind of very long success story in images has always been convolution, and today is still probably the most used in practice. And convolution basically works by sliding what's called like a kernel, which is this kind of square here, 3x3 square, around the image, and basically doing element-wise multiplication with the pixels. And if you notice what we're doing, we can basically do this because each pixel has a constant number of neighbors. So if you take any pixel in the middle, you always know that in the image you would have exactly 8 neighbors, excluding clearly pixel at the edge, but you can kind of pad zeros and solve this edge case. But usually you always have a constant number of neighbors, and also you have ordering of the neighbors. So you always know which pixel, given a central pixel, which pixel is on the top left and which pixel on the top right. And so you can learn this filter to give a certain coefficient to the top left and another one to the top right. So you can differentiate them. And this is what kind of gives rise to convolution. However, even though we want to, there is clearly an analogy between images and graph, because on graph we have nodes and node have neighbors, and also in pixels, a graph is actually a specific type. An image is a specific type of graph where each pixel can be connected to the adjacent pixels. However, graphs are more general, and in particular, each node can have a different number of neighbors. Not only as a special case here, but in general, you can have a node with 1 neighbor, a node with 2, a node with 3, a node with 1,000 neighbors. So really, it can vary a lot. And also, there is no ordering. There is no canonical order of neighbors. So there is no principal way of saying this is the first neighbor, the second neighbor, because you can kind of, if we reorder them, the graph is still the same. Whereas if you reorder the pixel of an image, the image clearly doesn't make sense anymore. And so we need to take these constraints into account, and this is what gives rise to graph neural networks. And how do GNN works? There are many ways of looking at them. One kind of common one is seeing them as message passing neural network, where to update the representation of a node I, we want to compute messages and send messages from all the neighbors, and then aggregate these messages. So here we're basically saying that we compute a message between node I and j, which depends on the current representation age I and age j of the two nodes. And then I will receive messages from all the neighbors, in this case 5, and we need to aggregate them in some way. So here we're doing aggregating them with a sum, and also transforming them based on the features of I itself. And then initially, this representation is clearly just set to the features of the vector, which is let's say a d-dimensional vector for all nodes. However, the problem is that, as I was saying here, here the initial value of age is features, and so here we are implicitly assuming that we have a vector of features for each node, and in particular that we have all the features for all the nodes. So we have this full feature matrix of dimension, number of nodes, time number of features. However, in practice, that is very often not the case, in the sense that in the real world, very often features are missing. So for instance, you can think of user demographics in a social network. We have an example here. So the red feature represents the age, the green represents the weight of the user, we may not know them for all the users because maybe they don't want to provide them. And right now, especially with the rising awareness in privacy, these information are available only upon consent. And so for this user, we may not know the weight. For this user, we may not know the age. For this user, we may not know anything. But still, we want to use the graph and the features that we know to do some sort of learning on the graph and to solve downstream tasks. We will see in a second. But this is just one example, but you can think of tons of examples where you have missing features. So if you think about a product co-purchase graph where the nodes are products and there is an edge when the two products are frequently bought together, usually the features for these products are product descriptions, but these are kind of manually completed by suppliers. And so if the supplier doesn't do that, you're not going to have a description for a product. And so this may be missing, but any metadata for the product may be missing because it needs to be completed. And in general, many cases where you don't have all the features for all the nodes, but you actually have for each feature is only present for a subset of the node in the general case. And it's not clear how to apply GNNs when you have this case of incomplete features. And it's kind of crazy that in the literature it's always never been tackled, this problem, even though if you ask anybody working in the real world, this is kind of what happens in most cases. So the question, the research question becomes, can we actually do learning on a graph where we're missing node features? And again, here the solve is to solve a downstream task, such as node classification, which I talked about before. So here I'm giving another example where we want to predict the kind of diet of the user. So whether it's an omnivore, vegetarian, or a vegan, based on these features, which are kind of half missing, and the graph structure. Clearly, we also need to know the labels for some of these nodes on the left. But in general, here, the important point is also that we are interested in the downstream task. So we are interested in doing well a node classification. We're not interested in reconstruct, not necessarily interested in having the best possible reconstruction of the features themselves. So we will see why this is important later, but just to give a hint, if let's say we reconstruct a feature and then we use a GNN graph neural network to do the prediction, if the graph neural network is not using some kind of information, it does not make sense for us to reconstruct it. And for instance, we kind of know the graph neural networks don't really use the high frequencies of the node features because that tends to be kind of noise in the features. So for us, it's not really helpful to reconstruct them, even though if you want to have the best reconstruction of the features themselves, you care also about these high frequencies. But for us, we only care about the final performance in the downstream task. So this is also what kind of differentiates this problem from the standard feature imputation, matrix completion literature, where the goal is actually just to reconstruct the missing values. So let's look now how we can actually learn with missing node features. So the simplest approach, so this is kind of, we're thinking of this problem, the first time, what is the simplest thing you can do? Arguably is, first having some imputation step, which is task agnostic and just, fills in the missing feature. And then you can use the graph and the full features and feed them into a graph neural network. And what are the simplest imputation approaches? So clearly you can think of, setting features, the missing features to 0. So we can see here the field features are kind of in a lighter color, lighter red and lighter green. So you can see here that the previously missings are now replaced by a 0. Kind of very simple, not so smart probably. We can replace them by a random value. So you can think of drawing some random value from a normal distribution. I guess in this case, you want the normal to probably be centered around meaningful value for your features. So, for the weight, probably you want, I don't know, something around 80, 70 or 80. And so here we're just kind of drawing random values. Something probably a bit smarter, you can say, okay, what about if I, for each feature, I take the mean of that feature, the average of that feature over the graph, and I always use that. So it turns out the average for the weight is 68. So all the nodes which have a missing weight we will now set that to 68. You can actually also think about now making use of the graph structure and a bit more fine-grained. Why don't we set the feature of a node to be the mean, but only among the neighbors? Because the graph structure, there is this assumption that if they're neighbors, probably they're more similar to each other. So let's only take the mean between neighbors. By the way, this graph is constructed. The mean of the weight is actually the same, but if you take the age, now we see that this node has a mean of his neighbors, which are this one here and this one here, it's 27, whereas the mean for these neighbors, which is connected to all these three, is 29. So now there's a bit more fine-grained imputation of the features. There is also some previous work which proposes some more sophisticated approach, even though it's kind of still a largely unexplored problem. So there are mainly these two papers that look at that. So the first one is called GCNMF, and the idea is to represent the missing features with a Gaussian mixture model, which is learned end-to-end with a GCN layer. And having a Gaussian mixture model, we can kind of compute the expected activation of the first GCN layer, and then the following GCN layers are just normal GCN layers. Another one is called partial Graph-neural network, and it performs a partial message passing, which only propagates the features that we actually observe. The problem with these two methods is that they suffer a lot in regimes of high rates of missing features. So when we have more than 90% of missing features, they really degrades substantially. In general, you observe that when you have, we'll see the experiments later, but when you have only 20, 30, 40% of missing features, it doesn't really matter what method you use. But when you go to higher rates, it matters drastically. And that is where our method really shines. And also, they don't really scale to large graphs, which is something we were also very interested in, and we will show how our method does that. So we will start introducing some notation. Don't get too scared. So we will have some maths now, but actually the final product is super simple. So even if you don't follow 100% the math, that's not really an issue. It's more for people that are interested, and it's going to be quick anyway. So we represent the node features are just a vector, and we split them in two. So the first part is x of k, is kind of k stands for known. So it's the features that we actually observe. And the second part of the vector is for nodes of which we don't observe the features. So u is for unknown. We do a similar split of the adjacency matrix. The adjacency matrix is kind of the matrix represented in the graph. So there is a 1 in position ij if ij are connected in the graphs, if there is an edge between ij. And again, here we can order the nodes such that the top left corner is only the adjacency between the nodes of which we know the features. The bottom left is between the nodes of which we don't know the features, and the other two parts are kind of between them. Then we define a degree matrix, which is basically just a diagonal matrix that tells the degree of each node, so how many neighbors each node has. Normalized adjacency, here is basically the idea that adjacency has 1 and 0. But if we want to, it's not great for applying this operator to features, so we need to normalize it. Common normalization is just to make each row sum to 1. And that's probably the most intuitive. Here is a slightly different version, which has some better properties, but I'm not going to go into details. But basically, this is very, very similar to just normalizing the adjacency to make each row sum to 1. What is important is the Laplacian matrix, which is defined as here it should be the identity matrix because it depends on how you normalize it. But here it should be the identity matrix minus the symmetrically normalized adjacency. But the intuition is quite simple. So the Laplacian operator is also widespread in physics, and what it does, if we take graphs, if you apply this operator to some features, it's just computing for each node the average difference between the feature of that node and its neighbors. So it's just telling you, how similar, how different you are from your neighbors. So that's all it's doing, and we'll see that it's going to help us a lot. So our idea is basically to do some sort of to do a reconstruction of the features, which promotes smoothness on the graph. So what smoothness means is that in order for a feature to be smooth, it should be kind of similar in neighbors. So it's the same idea of a function being smooth, so it doesn't change drastically. And if you think about, in 1D, I guess that's clear. In a graph, just means that the function shouldn't jump too much from a node to the neighbors. And this is also called the homophily assumption. Homophily is basically the same idea, that neighbors are more likely to share similar attributes. And this kind of smoothness on graphs is measured using a measure called Dirichlet energy, which is, you can just think of it as a way to measure smoothness. So the smoothest, the lower the Dirichlet energy, the smoothest the signal is on the graph. So here I'm defining this Dirichlet energy, which is defined as the quadratic form of the Laplacian. So x again is the feature, delta is the Laplacian, so is half of x transpose Laplacian, delta x. But intuitively, what this is doing is just computing some sort of squared difference between neighbors. So here I'm taking, for each neighbors in the graph, for each pair of nodes in the graph, this is their coefficient in the normalized adjacency. And I'm just saying how similar, how far they are. So clearly, if neighbors are very different, this means that the Dirichlet energy is going to be very big. If neighbors are very similar, so if all nodes have the same value for x, this is going to be 0, so it's going to be super smooth, clearly. So this is our way of quantifying smoothness. And we said that we want to promote smoothness. So the way of saying this is we want our unknown features to be the features that minimize this Dirichlet energy. So the other features we know, the xk, we know that we can't touch them because they are known. So it's not like we can play with them. We just want to we can just minimize over what we don't know. So we're basically minimize the Dirichlet energy over these unknown features. If we do, if we basically take this equation, compute the gradient and set it to 0, we can get a closed form equation for this xu. However, and it's this one here is not too important to look at the details, but what is important that this is very expensive to compute because you have to invert this sub Laplacian, which is kind of very, very expensive and is completely infeasible for nodes of any kind of modest size that we care about. So we need to find another way of doing this. But in general, we want to minimize the Dirichlet energy. So what's another way of doing it? Another way of doing it is basically to follow the gradient of the Dirichlet energy. And so clearly this Dirichlet energy is convex. So if we follow the gradient, we're gonna eventually get to a minimum. So we're basically doing gradient descent of this Dirichlet energy. So probably I won't have time to go into details, but this can also be seen as a differential equation with boundary conditions, where the boundary conditions are the fact that we basically in our differential equation, we let the unknown features to evolve over time, whereas the boundary condition is just saying that the features that we know, they basically don't change. So this is what is called a boundary because they don't change. And so as we evolve this and we follow this gradient, we can get to a solution for our unknown features. And again, you can derive, we can use Euler's method, which is the simplest method to discretize any differential equation. And by doing some derivation, we get to what is here bottom left, which is actually super simple. So this is just saying that in order to compute the next step of the features, and these at convergence is going to be the reconstructed features. So the next step is just a matrix multiplication of the previous step, and this matrix is actually very simple. So it's just the normalized adjacency where we replace the top k rows by an identity of some zeros. So this is actually even though the math can be a bit daunting, but in the end, this is just saying that in practice, what we need to compute this is just super simple. It's just a matrix multiplication. Another way of seeing this, and this is what we present in our algorithm, is probably even more intuitive. And it's saying, again, the idea here is we start with some x, which as the features that we know, they are to their true value. The features that we don't know, they can be set to anything. So we show that the solution at convergence doesn't depend on the initial values. We set them to 0, but you can set them to anything. Then what you need to do in your algorithm is this iteration here, but more simply can also is equivalent to multiplying your features by the normalized adjacency, which is just basically one step of diffusion, of graph diffusion using normalized adjacency. And then we reset the known features to their true values. So this step here will change the unknown features, but also the known features. But we know the known features, we know them. So then we at each step we reset them. And this also helps us guarantee that the final solution for the unknown features will not depend on their initial values, which is actually what we want, because otherwise it will be completely arbitrary. So this is actually, the super simple algorithm, which is super efficient because it only consists of this sparse to dense matrix multiplication. And in a number of steps, we find that 30, 40 steps are kind of always enough in the data sets we test on. This enables us to reconstruct the feature X in a way that is helpful for the downstream task, and we will see that now. So the intuition behind feature propagation is basically that it acts as a low-pass filter, and that's kind of the same behavior that we observe in most GNNs. So low-pass filter for it's concept from signal processing, but for people not familiar, it's basically the idea that we smooth the signal, we smooth the filter, the features, and basically by removing the high frequencies, which, as I was saying before, are usually the noise. And we observe that by this plot where the original feature in the graph, or this is the core dataset. It's this red here, and this is the plot of graph Fourier coefficients. So it's a plot in the spectral domain, and here we see that also high frequencies have still a reasonably high coefficient, and then the other plots are using feature propagation with different rates of missing features. And we see, especially in the case when there are a lot of missing features, this is completely smoothing the signal. So it kind of removes all frequencies. After this point, the coefficients are extremely reduced. So it only keeps the high frequencies of the signal, which is what is used by GNNs. So this is a part of our intuition why we think this works well with GNNs, because it keeps only the information that GNNs eventually end up using. So let's look at the experiments and to how well our method works. So first of all, just a single plot to be able to explain what's going on. So we have a bunch of baselines. So these are the baselines that I introduced as simple ideas. So setting the missing features to 0, to random, global mean, or just taking the mean of neighbors. And all these feature imputation method, which reconstruct the features, they're followed by a 2-layer GCN to then predict the node labels. We also compare it to the two more recent methods, GCNMF and PAGNN, and also to label propagation on the class labels. So this is a method which doesn't make use of features at all. So it doesn't really matter how many features are missing. And so it's kind of a baseline that tells us whether we actually need features and whether the reconstruction is helpful. In the x-axis, we have how many features are missing, going from 0% to 99%. And on the y-axis, we have the test accuracy. So our method is in yellow. So as I was saying, up to 40–50%, it does not matter that much what method you're using, apart from using random, which kind of performs terribly, but it does not matter that much. But then a gap, the gap really, really opens. And by the point where 99% of missing features, our method is the only one that has a good performance. And that didn't decrease a lot from observing all the features. So we can still do very well with only 1% of feature observed. Clearly, this is only Cora, so you may say, nobody in 2021 trusts Cora, and I don't either. So we evaluated on 6 common benchmarks. We also have actually results on another data set as well in the paper, which are the 3 standard ones, but also 3 much bigger data sets. So Amazon Photo, Amazon Computers, and OGBN Archive, which are kind of a lot more trusted. And we kind of observe the same behavior. Our method is always the one performing the best, and the gap kind of opens, especially as you have more features are missing. Here, I appreciate that it's hard to see the gap with, for instance, the gray line because it's so zoomed out, but the difference is, if you look at the numbers, is quite significant. And these are actually the numbers. So this is just focusing on the case of 1% of features being present. So 99% are missing, and the gap is just huge. So this is just comparing to the 2 more sophisticated methods, and you can see these numbers. So 20% plus here, and here as well here. On photo and computers, the gap are smaller, but still kind of very, very significant if you look at the standard deviation. And actually on OGBN products, which is the 7th dataset I was talking about, feature propagation is the only method that actually works, because the dataset is kind of big, which we will see in a second. The other interesting results is just looking at feature propagation and how the performance drops in numbers. So here we have full features, 50% missing, 90% missing, 99% missing. And in the parentheses, we have the relative accuracy drop from the performance with observing all features. And here we basically see that on average over these 7 datasets, the drop is only basically 4% of relative accuracy. So not even absolute, relative accuracy. So you can give up 99% of the features and still only lose 4% in relative accuracy, which I found very, very surprising. I was not expecting this at all. I was expecting the drop to be much, much bigger, which is actually what you observe with the other method. But here is basically saying, look, okay, features are important, but you can give up on a lot of them and still perform very well. So with 90%, you only drop on average 2.5%. So I think this is quite surprising results. Looking at speed and scalability, as I was saying, our method is also designed for being scalable. Here we have the end-to-end, the speed, the time it takes to train end-to-end. Our model and the other two previous methods, and our model is basically 3 times faster. And the interesting thing is that this also includes the time to train the GCN. And the time to train the GCN is actually what takes most of this time. If we only look at the time it takes to do the feature propagation itself, so the reconstruction step, that's actually super small. And in particular, if we take these other data sets, OGBN products, which is quite big, so it's 2.5 million nodes and 123 million edges. And these other methods, they don't even run on this data set. It only takes 10 seconds to do the feature reconstruction on a single GPU using feature propagation. So it's pretty fast. As a last question, we kind of asked ourselves, okay, I mean, works amazingly on these data sets, but does it always work? Or when does it work? Are there cases where it fails? And the kind of answer is that as feature propagation can be derived from an homophily assumption on the features, so we had this assumption when deriving it. We expected it not to work very well on a heterophilic graph where this assumption is not valid, and where instead neighbors tend to have different attributes. And so to validate that, we tested on synthetic graphs with different levels of homophily. So here on the x-axis, you have a different level of homophily, from 0 being kind of completely heterophilic to 1 being completely homophilic. And this is the performance without missing features. And we see that if the graph is very homophilic, feature propagation, even with 99% of missing features, performs almost as well as not having any missing feature. Whereas if the graph is heterophilic, then the gap is huge. So we can't really, it doesn't work that well if we have 99% of missing features and the graph is not homophilic. So here is completely heterophilic and the gap is pretty big. So some feature directions that, some open questions that we have. So it would be interesting to have a diffusion or a propagation, which is learnable end-to-end with the task. So at the moment, it's just fixed, almost a pre-processing step. So it would be good to have something end-to-end learnable. It would be interesting to do feature channel mixing. So at the moment, if you have multiple features, they are treated completely independently. So the diffusion is done on each channel separately. But clearly, you can think that a feature could be informative to reconstruct another feature. So it would be interesting to do this mixing. And also, this method only works on graphs that where you have a single type of edge and a single type of node. So it would be interesting to have an extension that works on heterogeneous graphs. So to conclude, we saw that missing node features is a very widespread problem, which has not been, there hasn't been that much attention to it so far. We derived an approach which is theoretically motivated and is robust to very high rates of missing features. So greater than 90% up to 99%. It is extremely scalable and fast, so it can run on graphs with millions of nodes very quickly. However, we kind of are aware of its limitations, and in particular, directly coming from the assumption that we made to derive it, it requires the graph to be homophilous. With this, I would like to thank you all, and I'm now open to taking questions.
Awesome. Thank you so much, Manuel, for the fascinating talk. We do have some time for questions. So please type your question in the chat. I can see that we already have a couple, but if you have any questions, I'll do my best to get to them. So first off, I guess a question more about just understanding graphs as in general. So the data and input to the algorithm is in the simplest case, a matrix with 2 columns, which determines the child-parent relationship, I guess the edge features, and rows are the nodes.
So usually you represent a graph, you can represent it in many ways, but the adjacency matrix is number of nodes times number of nodes. So it's square, and you have a 1 whether the node I and node J are connected in the graph, or a 0 if they're not connected.
Mm-hmm. Okay. And our next question is, when we refine the draft GNN model, so I guess a little further down when we have the data set, should we still need to emphasize weight from certain features?
Can you elaborate on that? So I didn't get also the second part, emphasize weight on features?
Yes, it says, do we still need to emphasize weights from certain features?
Yeah, I saw that in the chat now, but I'm not sure. So I don't know what is the draft GNN model, and I'm not sure what they mean by emphasize weight from certain features, to be honest. Okay. So it's a bit hard to answer.
Yeah, if you want to elaborate, Jihua, we could definitely try and answer your question. But for now, we'll move on to the next question. So does your algorithm get one large graph or many simple graphs, say, generated from images?
So the usual scenario is you have a single graph, and it can be as small or as big as you want. And we show that it works also on big graphs. And the graph, yeah, I mean, it can be anything. So it can be images, or it can be social network, or anything else.
Okay, awesome. And I guess they're really interested in seeing if there's a public GitHub for the method that you presented, and maybe some code that's available.
Yeah, so it's not yet, but it will be. So if for sure I will post on it on Twitter. Also, the paper is not available, is not public yet, but it will be in a matter of days. So I will share everything on Twitter as soon as it's ready.
Definitely looking forward to that publication. So our next question is, can you give us a few examples of different data input structures that you could feed into the network?
So if this refers to what kind of graphs we feed, so I can, for instance, talk a little bit about the data sets that we used. So these 6 data sets. So the first 3, so Quora, CiteSeer, and PubMed, they are citation networks. So the nodes are basically papers, and the edges are whether there is an edge if 2 papers cite each other, basically. And the features are some sort of embedding of the abstract. And also GBN archive is also a citation network coming from some different data and being much bigger than the first 3. Photo and computers, on the other end, are product core purchase networks. So taken from Amazon. So basically the nodes are product, and there is a link between 2 products when they are frequently bought together, and the features are kind of some information about the product. So I think it's also an embedding of the product description.
I'm guessing the photo is is it a data set of photos where nodes are just, those features would be like RGB, or is that?
No, photo is just a probably misleading name. It's just the name of the data set, but there are no photos. I think the kind of products in that data set are related to photo. So maybe they are like cameras, and computers are actually computer related products. But there are no images.
I see. Okay, so I guess our next question is more about I'll jump on to the last one actually. When dealing with graphs with millions of nodes, do you extract subgraphs before you run the algorithm, or how do you stitch if so, then how do you stitch everything together?
Yeah, so it's an interesting question. So actually, this method scales to very, very large graph in the sense that it's only, so I mean, there are 2 parts. First, there is the feature propagation algorithm, which reconstruct the features. And then there is the GNN that trains the model. So for GNN that trains the models, yes, there is a whole bunch of literature in how to train GNNs on large graphs. And usually what you do is called sampling. So you sample, each time you sample parts of the graph, and you only train on that subpart. And each epoch, each iteration, you sample different parts. And then and this is how you deal with this. For our feature propagation algorithm, is actually in most cases you don't need to do this, because it's basically just a sparse to dense matrix multiplication, and you can do it on the CPU. So you can you can have as big as a graph as your RAM basically enables you. So now we are working with basically very, very large graphs, and the bottleneck is just getting machines with larger RAM. Now, if you look on Google Cloud, there are machines they are expensive, but they get up to 10 terabytes of RAM. And I think with that, you could probably do you can do billions of nodes. But even more reasonable machines with 250 gigabytes of RAM, which you can easily get on cloud providers, they can still deal with kind of hundreds of millions of nodes.
That's really exciting, is the idea that we could start using really large networks, especially at Twitter. You guys are probably dealing with massive graphs. So our next question is on what types of features did your method support? Just to confirm, are you saying that only 1% of the population feature you can reconstruct the distribution of the missing features by just little bit of loss, about 4%?
Okay, so regarding types of features, I mean, pretty much anything. So we kind of work with continuous features. So anything that can be made continuous, but I'm quite sure it should also extend all the experiments are continuous, but it should also extend to categorical features. And basically, okay, so observing 1% of the features. So this is what I was saying before. So we don't actually care about reconstructing the missing features. So we do reconstruct the missing features, but we don't care about having the perfect reconstruction. All do we care about is then using this feature to solve a downstream task, for instance, node classification. So the 4% is a degradation we see in accuracy in the downstream task, not in the features. In the features, we actually is not the focus of the method. We checked; it doesn't do that well, because if you don't reconstruct the high frequencies, you can have a very high error. But these are not used by the graph neural network, so you don't really get anything by reconstructing them.
So I guess the feature propagation, it would just create a new node feature of its own that is used to train the GCN or the GNN downstream.
It reconstructs the features that are missing, but yeah, it does that by only reconstructing kind of it does reconstruct all the features, but only the component of the features that you care about. So if you look at it from a signal processing point of view, only the low frequencies.
I see. So it's not about completeness; it's more about importance of features.
Yeah, exactly.
That's really interesting. And I guess to follow up on that question, have you looked into kind of different downstream GNN models that might work better or worse? I think you mentioned that you guys did like a simple GCN with two layers. Is there any research into graph attention networks or other models?
Yeah, so we also tried with Graph Sage, which is another model. Basically, you can use any GNN. We use these two because they are two of the most popular, and they let's say the kind of challenge with graph attention network is that it's much harder to train and tune than these other two. And in our case, if you look at this table, the number of experiments that goes in here, they are in the order of thousands. And so if you have a method that is kind of very hard to tune, it kind of makes it impossible. But we are kind of confident that the results would extend to graph attention network as well.
I see. So it's really stands on its own. That as long as there is homophony, then it's likely to perform well. I see.
Exactly.
And our next question would be, could you give some intuition on why low pass filter would produce more stable results than local average? Intuitively, it feels like a local average would already be about as smooth as possible.
Yeah, this is quite an interesting question. I also got this from reviewers when I submitted the paper. And the intuition is that if you doing just the average of the neighbors, it's kind of one-step approximation of feature propagation. So feature propagation, you do this diffusion in the graph multiple times, whereas neighbor average is like doing some sort of diffusion only once, where you diffuse from your neighbors to you. What this means is that it's perfectly fine if you have, only 50% of missing features, because you still, on average, each node has kind of 50% of the neighbors have features, and taking their mean is good enough. However, if you have a lot of missing features, it may be that in your neighborhood you only observe very few features. So if you estimate taking the mean, you have a very high variance because you have very few neighbors. And probably more interestingly, it's the case where, and it can happen very often if you have 99% of missing features, is that none of your neighbors has the feature. And so in that case, the neighbor mean, doesn't work. So we set it to 0 if none of the neighbors, because it's kind of undefined, the mean. So we set it to 0. Whereas the feature propagation, by propagating multiple times, it allows to aggregate from further away in the graph, so from multiple ops. And so it works also in the case where none of your direct neighbors have the feature.
I see. So, okay, so it's n hops away, and also like it also focuses on the most important features as well for n hops away. Okay, that's very fascinating. This is I definitely understand like GNNs personally from like a model, like the modeling side, but actually the reconstruction of the graph it's an area that's really interesting, and I want to look further into. I can't recall the name of the paper, but you mentioned I think it was multi-channeling. There was a paper I read recently about dealing with heterophony.
Heterophily.
And how they proposed a method that kind of was able to outperform a method that could reconstruct the graph in a way that later on for downstream tasks it was able to perform better, even though there was a lot of differences. Is this something kind of like a combination that with your method and that method you guys would look into to that could address that?
Yeah, possibly. There is kind of an emerging direction just in general on graphs with the low homophily, so heterophilic graphs. In the last year, especially, there have been a lot of paper, and I've started looking into them. So one of the directions I'm kind of excited about is whether we can make this work for non-homophilic data. And one way of doing that is also kind of mixing the feature channels and using some more complicated aggregations.
Yeah, I definitely look forward to seeing that. And I guess our last two questions, one of them is about the slides. I'm guessing this will be available once the paper is published.
Yeah.
Awesome. And our last question is more in general about any suggestions you would give us in terms of conferences or tracks in research blogs where we could learn more about the latest GNN research.
So for me, to be honest, it sounds like advertising my company, but actually, Twitter is kind of, to be honest, the platform where most researchers in ML share their work, or at least in GraphML. So I kind of get all the new papers from Twitter, but just following the main researchers. Otherwise, there used to be workshops on graph neural networks at all the main conferences. Now, not anymore, because they are becoming so widespread that there are too many people for a workshop. But there are talks at every conference on graph neural networks. For people getting into the field, I recommend there are two super nice blog posts from Distill, which is this kind of online journal that makes amazing, very pedagogical blog posts about many machine learning concepts, and they recently made two about graph neural networks, which I can share here, and they are actually amazing. So for people that are new to them, it's I think it's a great way. So this is one, and the other just if you go to the main page, you can see that. But yeah, this is pretty much it.
I definitely agree. I had a chance to check out the introduction article, and also I think it was more about how the mathematics of GNN. And it was, I love the diagrams that they also provide, and I definitely agree with Twitter being the best resource. And also probably following you and Professor Michael Bronstein who are experts in the industry and in GNN.
Yeah,
so
Michael more than me for sure.
That should be it for the questions. Thank you so much, Emmanuel, for joining us today. I really appreciate you taking your time to answer all the questions as well. And thank you everyone in the audience for joining us.
Thank you. It was a pleasure.
Awesome. Have a great day.